Hi there, Physics 131. So I just want to take a quick look at today's reading, Class 12, which we're finishing off Chapter 4 today, actually. So Chapter 4, Section 4.5 is on projectile motion. So, and this is similar to free fall, actually, in that there's only one force on the object, which is gravity. So something's in the air, and it's just has force of gravity, so it's flying along pretty quickly usually. But in projectile motion, I guess there can be a horizontal and vertical motion. And there's independence of horizontal and vertical motions. This whole idea that it's the same time in both cases, but you calculate the x and the y separately. So and you use the equations of kinematics for all of these things. I would go through this. The idea is that always the x, so if you set x to be the horizontal direction and y to be vertical, then the acceleration in the x direction is 0. So vx is always the same. But the acceleration in the y direction is that negative 9.8 meters per second squared. So it's always decreasing or getting more negative. And then the quantitative analysis, again, these are the equations. So the x component is just a sub x equals 0. So there's really only the one main equation for that, which is that x is the x initial plus this constant velocity, which is sometimes the initial velocity magnitude times cos theta, where cos theta is the angle above the horizontal. Sorry, theta is the angle above the horizontal that the projectile was launched. So cos theta times v0 is the x component of the velocity, and sine theta times v0 is the initial y component of the velocity. And for the y components, you have all these equations of constant acceleration that we used actually way back in Chapter 2, which is the v final is v initial plus a times t, where a is now negative g. Y is y initial plus v 0t plus 1/2 at squared, where again that's all g's in there. So it's the same time on the x and the y, same little t, but you do the equations separately. And so there's an example: best angle for longest distance. You want to throw a rock the best horizontal distance, sort of a range, I think. They come up with this equation. So, and then I think, so this is really the equation that you get. It's sort of, you should be able to get that. The question is, when is that maximum? And they argue that it's 45 degrees. And it's a bit of a tricky argument. But you can just calculate it out. If you try the same speed, but try a 30-degree angle or a 60-degree angle, you should always get less. So it's kind of a good thing to know. If you're going to throw something, let's try to make it at an angle of 45 to get the farthest distance. Something about human cannonballs. Again, initial velocity is given, initial angle is given, and you're asked to solve for something. I think in this case, determine the time that Stephanie spends in flight, determine the horizontal distance, where the net should be placed so she lands safely. So again, this is all pretty practical stuff. And the last section, 4.6 from Chapter 4, is called Starting and Stopping a Car. And it's all about this whole thing about rolling without slipping. So she makes this argument that right at the very bottom of the wheel, even if the car is going along, the tire, the bottom part of the tire where it touches the ground is not moving. So that if you actually keep going and look at a force diagram for a car, the friction force that you put is usually the static friction. Remember, when you deal with friction, you have to make a choice to use kinetic friction or static friction, depending on if the surfaces are sliding. So with a car, you might think it's a bit unclear, but the idea is that if the wheels are rolling along without slipping, like you're not screeching along, then it's actually the static friction of the road on the car that acts on the car. So we'll talk a lot more about that in class, but that gives you a start in the reading. Okay, bye for now.